Can you hear me? Yeah, I guess so. So I will be walking during the presentation, so feel free to tell me if I'm not heard well at the end. So I'm a software engineer. I did some data science. Also had some free time recently, and I like learning things, especially learning things the hard way. So when I had this free time, I decided I will read some books and I will learn how to understand deep learning. So I also watched some videos, and after some time I could say, like Donald Trump, there is nobody like me who knows more about deep learning. But then, so what is the deep learning? I will get, oh, it's not working. So what is the deep learning? It's a kind of powerful machine learning model that can approximate almost every function, almost. Inside, it's just a deep neural network, and it's kind of good on recognizing patterns. And, oh, wait, it's relatively quick to learn, to teach the model with massive amounts of data. And it's good at recognizing patterns, and this is what makes it very efficient for speech recognition, natural language processing, image recognition especially. Okay, that's all about deep learning, because I think that 1/3 of this conference is about deep learning, so that's all you need to know. So I want to talk more about reinforcement learning. And you know what is the reinforcement learning famous for, right? It's the Atari games played by the computer. There are also some other examples, like AlphaGo, like autonomous vehicles, or the games, of course. So, so in reinforcement learning, we teach machines how to act by trial and error. Okay, to understand a bit more or more formally, there are two examples to understand reinforcement learning and trade-offs in it. So first one is the multi-armed bandit problem. So we assume that we've got casino, and there are slot machines, like 4 here. I enter the casino and I don't know which one to play. So I need to choose one to play, and then I will have some reward if I win the game. But at the beginning, I don't know the underlying distributions of the slot machines. And also, I iteratively repeat the process. So I will play forever in this casino. And what I want to do, of course, is to optimize my rewards over time. Second example is the maze problem. So I'm in a maze, I can move left, right, front, back, and I need to find the way out. So that's kind of similar. I've got some state, I need to take actions, and I've got some reward either now or at the end of the maze. And maze is deterministic, while multi-armed bandit is non-deterministic. Okay, so after this intuition, we can introduce some concepts. So first concept is an environment. So environment has some state that I know or I don't know. I can reset it to the initial state, and I can take some actions. And with each action, I will get some reward. So there is actions, rewards, and there is return. Return, which is usually some kind of sum over rewards I got at each state. Okay, so so generally, reinforcement learning is solving problems that are specified by the environment by using the actions, and my goal is to optimize my return. So what do I need to do this? And there is like the most important concept in reinforcement learning when it comes to solving the problems. It's Q function. So Q function is a simple mathematical functions that, given a state and an action, will tell me what is my expected return if I choose this action. Right? So actually, if I know the Q function, I know how to act in this maze. I just need to optimize my expected reward. Yeah. So every time I see a state, I ask the Q function, what's the best action for this state, and I choose the action. Of course, I don't know the Q function because, like in the maze, I'm in the middle of the maze. I don't know where is my goal, and I don't know if going right or left is better for me. What's the expected reward? Sorry, return. But there are some small games, and I can compute the Q function. I will just go around the maze, and I will update iteratively the Q function. And many of the Q function will converge. Like if I use the procedure as on the slide, like I set QS of A to be equal to the reward I get plus the expected reward I get from calling the same function, I will, if I use this procedure, my algorithm will converge to the true Q. I can use also more smooth version of updating Q function, and it's very helpful if the Q is non-deterministic or if the step in environment is non-deterministic. Okay, so what's actually deep reinforcement learning? So it's just learning Q with deep learning. So Q is like there is too many states to know the Q, but I can try to approximate it with deep learning. And coming to the end of the long introduction about what reinforcement learning is and which problems it solves, I need to tell you about two main directions in reinforcement learning. So one is towards universal intelligence, or we may call it AI. And this is, we want to create an algorithm which is going to learn very fast a new environment and will be good in playing in this environment. It's like I will teach my algorithm on a single Atari game, and I want it to learn the new game very much faster than learning the game from scratch. Okay, so that's the direction towards general AI. But there is also another direction in reinforcement learning, and it's I want to solve real problems with reinforcement learning. So I will create my own environment, I will create the rewards, and I expect that the outcome of the play in the environment will be usable in other applications, like autonomous driving. So following that direction, I started to think about how to solve the cube. And it is the hard way, because actually when I use tutorials to learn something new, in tutorials everything is simple and everything works. And when I solve some hard problem, I understand that in real world nothing is simple and nothing works. Okay, so let's talk about the cube. So the cube has really a lot of states. You can see it on the screen, and the number is so big that we could encode every word in a single state of the cube, or actually every word in every language, and there is still space in the cube for two long numbers, right? So you can see that's to the power 10 to the power of 19, like enormous number. And why is it interesting? It's interesting because I can solve every cube in 20 moves, or 26. Depends on how do you count it. Okay. And also the basic algorithm that you know from, I don't know, from school or from internet, it's usually about 120 moves. So if you start with one wall, then you start with first layer and so on, it's usually about 120 moves. And what's interesting, that we know that the cube is solvable in 20 moves, but we don't know how unless we use brute force. And that's actually how people proved that it's 20 moves that is enough, because they have just like enumerated all the states, and for each state they observed that it's only 20 moves. Okay, so I started like taking tutorial to reinforcement learning and trying to create an environment to solve the cube in the optimal way. And what was actually the result? So I created the rewards, 1 when it's solved, 0 when it's not. I like coded the cube. Like cube is just 6 walls. Every wall is 3 times 3. And every square can be in one of 6 colors. So it's a tensor like this. And I also needed to define actions. So action is just choosing a wall and then choosing a rotation, left or right. 12 actions. So of course it turned out to perform totally badly. Like, because what is reinforcement learning? Reinforcement learning will go through the states of the cube, and if it solves, it will get reward. But actually, you know how much states there is. So solving by walking randomly on the cube is totally impossible. So yeah, so then you realize that actually deep reinforcement learning is not a solution to all problems we have. And actually, it's not a black box. So I was thinking, what can I do better? And there is 2 pills, blue and red. In red one, you can tune the parameters of underlying neural network. You can add more CPUs and GPUs and add more layers to the network. Or you can choose the blue pill. But let me say you why the red one is bad. Tuning parameters is almost every time bad if you don't know what's going on underneath. And adding CPUs and GPUs makes the problem more complex, or you don't understand what's going on these CPUs. And it's the same with layers in the network. So what I did was I dig deeper into the algorithm. I also tried to solve a smaller problem, like a cube that has only two squares on each side, and scramble the cube only, for example, 3 times. Like, yeah, you can imagine that. And also, I could see what others did. And at the end, you come to think, what is actually the tough part of the problem? Okay, so first, how we train the underlying network. And that's, so you probably know that we train the neural network in batches. So I take some batches, I compute the gradient, and I change the weights towards the better solution. Let's assume I've got a maze like this, so it's actually binary tree, a full one. Not every edge is on the screen, but it's working like this. You can go left or right, and to get the reward equal to 1, you need to go first right and then left to the end, or first left and then right forever, like. So what happens if my batch size is 3, let's suppose, and I'm in the state A? So I'm going another few steps, and I'm teaching the networks with my last moves, which were good, and they were all left. So what is the neural net learning? It's learning that there is some state, but actually going all the time left is a good strategy. And then I choose a batch after going to the B state, and I try to teach it with going all the way right, and I train the network like going right is the good strategy. So it will never converge. So we need to think at the beginning how we train the network. So there is something that is called replay memory. So it's not the case that I'm walking in the state space. I'm just having some memory that I put states or actually transitions to it. A transition is a state, an action, the next state, and the reward. And I use the states sampled from the memory to train the network. And memory is actually just a cyclic buffer of transitions. Of course, I need to use random batches. And when I do this, what happens to my cube? How is my neural net solving the cube? So I've got some state. This is an action. I've got next states. I get some reward. And this 4 is the transition. So I will put every transition in memory. Then I sample it. And then I try to teach my network with the samples. So first of all, I need to think of the exploration versus exploitation trade-off. So if I've got, for example, almost everything solved in the cube, like first wall, I've got 2 walls, and then in cube, sometimes I have to break some walls to solve it. So I need to explore states that appear not to be optimal for me. And what that means is that I need to have in memory states that are close to being solved, because I want the network to learn about the states that are close to being solved, because these states give me much more knowledge. And also, what's different in Cube to Atari games is actually in Atari games, when you play bad, you will lose fast. In Cube, if you play bad the cube, you will never finish it, right? So playing bad means you will play a lot of time without any reward, while playing good gives you like quick reward. So the situation is a bit different. So I added also a max steps parameter. So if my neural network tries to solve the cube in more than, for example, 10 moves, I will just restart it I will say it's not solved. And to understand what is going on, I will speak a bit of the algorithm. So how I choose the next action to take. So with some probability, I will choose a random move. And this is because I want to explore different states. And at some probability, I will just choose the best action that is chosen by my model. That is quite simple. And also, I want to have something like, with time, the probability of going randomly decreases. And the main loop of the algorithm is I have some state, some starting state. I reset the environment. I get the state. I choose the action. I have next state, reward, and I know if the game has finished. I will push this transition to memory. I will change the state, and I will optimize the model. That's like how I train the network. And what else I need? I've got some deep Q network underlying. So, and I've got some parameters of learning. So I need to think, how does the random walk probability decreases over time? I need to think, what is actually my reward of choosing any action? And I also want to tune the batch size and learning rate. Okay, so we can also think of tuning the model. And usually we start with 3 linear layers. We can try adding some convolution, some batch normalization, dropout. These are standard techniques you do for deep learning. But, oh, yeah, you can also tune the parameters carefully. But after thinking a bit of it, it turns out that setting the rewards is more important. Because if I have only 0 or 1, actually the algorithm needs to learn 25 moves to get to the reward. That's clearly too many moves. So you try to add some rewards, negative rewards with every step, or you want to think of how many % do you have to solve the cube? Like, you can calculate it in 2 ways. Like this, I've got, this is fully solved wall, this is fully solved wall. This one is, I would say, around 60% solved wall, right? So I can say it like this, or I can compute the number of walls that are solved. But actually, I checked both, and it turns out that both these rewards appear to be bad in training, because they actually tell us they are meaningful only 2 moves before finishing, because yeah, you can think of it, why this reward is bad. And at the same time, you want to minimize the number of moves. And there is yet another problem when you start to analyze what is the cube and how should this neural network learn to solve the cube. You understand that the representation is kind of hard also, because you start with one encoding colors, because usually one hot encoding is better than plain numbers. But then you realize that the states you get are not very, they are changing in a weird way when you represent it this way. Because you want to represent the cube using the symmetry, and so that learning simple algorithms is easy for the cube. So what are the results? So one word is disappointing, I would say, because you will have my code, so you will be able to see it. You can have like solving cubes, for example, for 5-6 moves with some high probability. I found a paper or a blog post that the guy is saying he can solve 8 moves, but he's not using reinforcement learning, just traditional deep learning. But there are still some takeaways from this experiment. So first, right now, I will publish my code, so you have almost everything to start experimenting with reinforcement learning. There are also other environments which are simpler. You don't need a GPU for that, actually, because what I observed that in deep learning, in many cases, you need a lot of GPUs. And in reinforcement learning, it's often the case that there is changing the states and making the actions takes a lot CPU. You cannot move it to GPU. So it starts to be a bottleneck. So from switching to GPUs, you get speed up like like about just 3 times faster. That's not that much. And there is still a lot to do. Like you can improve the solving how to solve the cube, and like there is why to do this, the question. So I think like looking at the job offers right now, so most of them say that we are a company building some software and we use a bit of AI. So, and actually this AI is like the sport tires in a Cinquecento often, and it's gonna be different, that there will be no software without AI, and so it's good to understand what's going on underneath. Yeah, and last thing, a few things that were great. There is a course on Fast AI website that is, I would say, great. And if you have, like, for me, it was better than watching serials in the evenings, because this guy is doing something. Oh, we've got a Kaggle competition that was run 2 years ago, and actually the top 20 solutions were very hard, like ensembles of different models. But I will show you a solution using deep learning in 20 lines of code. And he shows you it, and like it works. There are also some posts on Medium. You can see Emergent Future. There is like a tutorial for reinforcement learning, and it's quite good. And there is a lot of stuff in PyTorch, Keras, TensorFlow tutorials. And there was a deep RL bootcamp on Stanford or Berkeley, I think. So there is a lot of videos there. And you can check my GitHub tomorrow when I publish the code. We've got still 2 minutes, right? Or no?
Yeah. Any questions?
Oh, no.
Okay. Maybe one question would be.
Hi. Hi. Did you try, like, gradually increase the difficulty of initial steps in your training procedure? Because it's like seems natural to train a network at the beginning with a simple cases, simple states, and then like move towards.
Yeah, so I did it. So I trained my network at the beginning with, after scrambled the cube, only two moves, and so on, 3, and so on. Yeah, and then I kept in the, there were not many technical details in the presentation, but I kept in the replay memory, like I wanted to balance the states that are in the replay memory, so that all the time there are some states that are very close to being solved, because I didn't want the network to forget about them.
Okay. So yeah. It gets stuck around 6 or 7.
Yeah, because that's the problem with the states. You've got 12 states that are 1 step away from solved. 12 times 12, 144, 2 steps, and then there is much more steps with every move. So yeah.
Okay, thanks.